Hi, in this video, I will talk about joint synthesis of safety certificate and safe control policy using constraint reinforcement learning. I am Haitong Ma, and I'm a incoming PhD student at School of Engineering and Applied Sciences, Harvard University. This work was done during my graduate study at Tsinghua University and jointly done with Robotics Institute, Carnegie Mellon University. And this work mainly focuses on the energy function-based safety certificates. The energy functions were widely used in control scenery to prove important properties such as safety, stability, and reachability. The desired system states, such as safe states, should be assigned with low energy, and the system will convert to the desired states if the energy is dissipating. This is actually the main idea of these energy function-based methods. For example, the Lyapunov function, the control barrier function, and the safety indexes in the safe set algorithm all belongs to energy functions. In this figure, for instance, these unsafe states should be assigned with high energy, and our goal is that the system should always stay in the desired state set, which is also a forward invariant set, and the states inside this set should be assigned with low energy. After we have the safety certificates, we could use them to synthesize safe controllers. First, we have a safety specifications. For example, the robot should always keep a safe distance from human. We could use it to synthesize a safety certificate file. And if you have the dynamics module, we could easily obtain the control safe set. And the control safe set should satisfy the feasibility requirements that dissipates the system energy. After that, if we also have a nominal controller, we could use it to synthesize the safe controller. However, in this way, we must know the dynamics model or the nominal controller, and we must guarantee that the control safe set satisfy the feasibility requirements. These requirements actually pose great challenges on how to synthesize the certificates and the controllers without known module or known nominal controllers. Many studies have used learning-based approaches to handle these challenges. So some study learns feasible energy functions. However, they usually assume that they have prior dynamics modules or nominal controllers. Some also use learning-based methods to learn safe control policies. However, they usually assume that they have a feasible certificate. A recent study proposed a joint synthesis algorithm. However, their approach is more intuitive. They just iteratively update each one, and there is no solid convergence guarantee. So to summarize it, the real challenges in joint synthesis of certificates and control policies is that the certificates and control policies are actually closely related to each other. And so if we do not do either of them, we can't know that our certificate is feasible and our policy is safe. So it's more like a hen-egg paradox. Let us first explain the problem formulations. So in learning the feasible safety certificates, the most important thing is that we must guarantee the persistent feasibility, such that there must exist actions to dissipate the system energy. According to the feasibility requirements, we could formalize a loss function to learn safety certificates, that we optimize the safety index parameters so that to minimize the inevitably energy function increases or the constraint violations of this inequality constraint. For learning the safe control policies, we actually use the constraint reinforcement learning to learn safe control policies. Here, the constraints are posed on each state. And for this problem, we used a Lagrangian-based solution with multiplier network proposed in our previous study. Notably, this problem formulation is different with traditional constraint Markov decision process formulations. And typically, all previous constraint reinforcement learning use this problem formulation. In the constrained Markov decision process setting, constraints are posed on a single Markov decision process. So the constraint is irrelevant with the state. And if we use Lagrangian-based methods to handle it, here the Lagrange multiplier is just a scalar. However, in our case, the Lagrange multiplier is relevant with states. So we use a neural network to approximate the mapping from the states to its corresponding Lagrange multipliers. Okay, a small summary is that we have two problem formulations. One is certificate learning and the other is policy learning. So how to unify these two learning objectives in our algorithm? Our solution is the joint adversarial optimization. First, we prove that we need to unify the loss functions. We prove that in the policy loss function, if we have the optimal safe policy and optimal multiplier pair, this optimal multiplier actually also filter out the constraint violation terms, just like what we did in formalizing the safety certificate loss functions. Therefore, we could get these linear correlations between the two loss function terms. Therefore, if we further use the envelope theorem, we could unify the policy and certificate learning in this joint adversarial optimization procedure. Intuitively, the in loop is actually the policy learning part where we maximize to get the worst case energy increases. And the outer loop is actually the certificate learning process, which where we minimize this worst case energy increases. The result of this adversarial optimization is actually that our worst case energy increases converge to zero. So actually, this means we get the feasible safety certificates and also the safe control policies. And in our paper, we also provide solid convergence guarantee. You could check the paper if you were interested. So we conduct experiments on the safety gene, commonly use the safe reinforcement learning benchmarks, where the agents must avoid hazards to achieve the goal. We use the safety index parameterizations in another previous study. We compare our baseline algorithms mainly with a empirical energy function or empirical safety certificates. Another is we directly use the safety specifications as the energy function or common constraint reinforcement learning algorithms provided in the safety gene. We compare the episodic violations on tasks with different hazard size. This environment actually has small hazards and this has larger hazards. So in the training results, our proposed algorithm actually guarantees safety or the zero violations on both sides of hazards, while the empirical safety certificates only works on the smaller hazards case. For the larger hazards case, there still exists constraint violations even after convergence, which means that we actually learn feasible safety certificates and solidly safe control policies. As for other baseline algorithms, they have difficulties achieving zero constraint violations. Moreover, we also want to visualize the forward invariant sets on a simplified environment. This red line is actually the boundary of the real maximum forward invariant set. This set is numerically solved by the Hamilton-Jacobi reachability analysis. So notably, states outside this red line is actually the forward invariant set. So before synthesis, the invariant set is actually the green line. So we could observe that there still exists some unsafe states in this invariant set before synthesis. So this certificate is actually not feasible. So however, after Synthesize, we actually get a feasible subset of the real maximum forward invariant set. This actually means that we could learn a feasible safety certificate in our algorithm. Okay, finally, to summarize this presentation, joint synthesis of policy and certificates is hard since this is actually a hen-egg paradox. We do not know a prior certificate or policies. And we use the adversarial optimization with unified loss functions to handle this paradox. And our open source implementation is on this GitHub repo. Thank you for listening.